Okay, hi. So I'm Lois. I'm a PhD student just finishing up at Imperial College London, and I work with Ali Mashayek. I'm going to talk about some of my PhD work, which is on representing topography not for internal tides, but for oceanic lee waves. How do I make it? It's supposed to work. I'll just click. No, it shouldn't. Okay. All right, thank you. Okay, so just a quick introduction. We've had a nice introduction today already, but lee waves are steady internal waves that are generated by stratified flow over rough bottom topography in the ocean and atmosphere. And I think this is actually a very similar satellite image to one which was shown by Jorg earlier of atmospheric lee waves over the Adriatic Sea. So I've mostly been focused on lee waves in the ocean, but it's a lot easier to show an image of lee waves in the atmosphere. So just to set up some of the parameters of the problem, we have some bottom topography, so a mountain or a ridge or a seamount of characteristic height h. We have some background velocity u and some background stratification n squared, which we'll consider to be uniform and constant today. That's not necessarily the case. And then when that flow interacts with the topography, you get a vertically propagating internal wave. And we care about these lee waves in the ocean because they extract energy and momentum from the mean flow and transfer it to smaller scales where mixing and dissipation can act. And in particular, lee waves are an important sink of energy and momentum in the Southern Ocean because of the interaction of the energetic mesoscale Eddy field of the Antarctic circumpolar current interacting with very rough topography in the Southern Ocean. So this is a figure reproduced from a study by Nick Rush and Ferrari in 2011, where they calculated the energy flux into lee waves. And you can see there's a really high band of lee wave generation in the Southern Ocean, and in particular in the Drake Passage, where there's a real hotspot of generation. But these lee waves are on the subgrid scale of global ocean models, so we need to parameterize their effect on mixing and drag. So how do we represent these lee waves in ocean models? Well, the first step is to estimate how much energy is converted from the background flow to the lee waves, so a kind of generation problem. And then once you've estimated that, then you need to decide how that energy redistributes. So do the waves break locally and you have abyssal mixing and dissipation? Do they propagate elsewhere? And then how do they break? Do they break through wave interactions, for example, or do you have wave mean interactions? But I'm going to focus on the first question today. So the question of generation. So if we know some background velocity near the bottom, u and v, we know some background stratification n squared, and we know some representation of the bottom topography, say h of xy, then we could just plug those into a linear theory and calculate their energy flux. And so my focus is going to be on the bottom topography as a part of this kind of recipe. So this is the expression that you can derive using the linear theory for energy flux. So E is the energy flux. Notice this is a double integral over horizontal wave numbers K and L. And we're assuming steady, horizontally and vertically uniform background flow. Again, perhaps not a good assumption. And one thing to notice here is this term under the square root. And what this means is that the energy flux is non-zero only when u dot k, which is the intrinsic frequency of the waves, is between f, the Coriolis parameter, and n, the buoyancy frequency. So effectively what that does is it sets a range of horizontal scales on which your propagating lee waves can be generated. So say the horizontal wavelength lambda is between 2 pi u over n and 2 pi u over f. And in the ocean, that might be between about 1 and 10 kilometers. So what it means is that if you have very narrow topography, then you don't generate propagating waves. If you have very wide topography, again, your waves are evanescent. So it's just this intermediate range of scales at which your waves are generated. And it's the scales of the topography that sets the horizontal wavelength of the waves. And the way the topography comes into this expression is through this P of KL, which is the topographic spectrum. And notice that only the radiating wave numbers, so within that range that I showed, contribute to this integral. So how do you find P? Well, if you know the topography, h of xy, then you could derive it directly from the Fourier transform of that. There are a couple of problems associated with this. So the first problem is that we don't even know the oceanic bathymetry at sufficient resolution to do that. So our knowledge of the oceanic bathymetry comes from the highest resolution we have comes from multi-beam surveys from ships that actually go out and in situ take surveys of the seafloor. And that might be at around 1 kilometer resolution or less. So that's going to be sufficient for predicting this lee wave energy flux. But elsewhere, we have to rely on satellite altimetry-based estimates, which don't have high enough resolution, so maybe about 6 kilometer resolution. And there are ways around this. You can have statistical estimates of the abyssal hills in the ocean, but that's a big problem, but not one I'll talk about today. And then the other problem is kind of similar to the last talk. We're using a linear theory. And if we define a Froude number, which we define here as NH over U, where H is the characteristic height of topography, the linear theory only applies when that Froude number is much less than 1. And for some typical oceanic parameters, that might mean that when your topography is less than 100 meters tall. And we know that that's not the case everywhere in the ocean, certainly. So we know that our linear theory won't apply everywhere. So we need to deal with that. So the motivation for this study is that we have idealized studies, so modeling studies with synthetic topography at just lee wave radiating horizontal scales that have shown that linear theory can predict the energy flux into lee waves, such as this study by Nakash and Ferrari in 2014. But estimates of dissipation from microstructure observations in the Southern Ocean, for example, suggest that linear methods do actually overestimate lee wave generation. So there's quite a bit of evidence for that. So what we want to do is understand how useful these parameterizations are in a more realistic setting. So when we have time and space varying flows, and in particular with complex large amplitude topography. So what we've done is used a realistic wave resolving model of the Drake Passage, so this hotspot of lee wave generation, to look into whether we can use these linear parameterizations kind of in reality, where our model is kind of reality. So the question is, if we know some realistic and finite amplitude topography and flow, can we predict the lee wave energy flux? So this is kind of the outline. On the one hand, we have simulations. So we have a realistic simulation of the Drake Passage with a resolved wave field. We then have to filter for the wave field to take it out from the other parts of the flow, and then we can calculate the energy flux. And we're talking about the energy flux near to topography. And then on the other hand, we can think about parameterizations. So if we take the modeled large-scale flow from the same set of simulations, and we take the bathymetry that was given to the model, then we'll use 2 different methods, which I'll explain briefly in a moment, for representing that topography. And then we can calculate the energy flux, and then we can compare the 2. So these are the simulations. This is the domain that I'll be talking about. It's nested within a larger Southern Ocean domain. It's run using hydrostatic MIT-GCM at 100th of a degree resolution, which is about 600 meters to 1,200 meters resolution. It's got 225 vertical levels at less than 25 meters. So we're just about resolving the lee wave field, although perhaps not all of it. One thing important to note is that we don't have any tides in the simulation, so no internal tides to complicate things, although obviously they might change the nature of the lee wave generation in reality. And we have a fairly realistic bathymetry because lots of ships have gone to the Drake Passage and taken multi-beam surveys of the topography there. And I'm showing just here the sea surface temperature. And I won't be talking much about the surface field, but you can see there's some really beautiful submesoscales, and Pauline's going to be talking about that in her talk. But my focus has been on the lee waves at the bottom of the ocean. So the first thing to do is we need to filter out the waves from the rest of the flow. And so on the top here, I'm showing zonal velocity, and on the bottom, vertical velocity. So in vertical velocity, you can actually see most of what we have there is the lee waves. So they're being generated at the bottom, propagating up to the surface. And in fact, they're actually reflecting back down again here. Whereas in the zonal velocity, you can see the main signal is from the mesoscale eddy field. So how can we separate the wave field from other similar scale processes? So we could use a temporal filter, but actually in this case, that's not going to work because the lee waves have the same frequency as the flow that generates them because they're phase locked to the topography. Or a spatial filter. So as I mentioned before, you have this known range of horizontal scales on which your lee waves can be generated. So you can use that. There are lots of other processes that occur at those kind of scales, like submesoscale processes. So we developed a spatial filter that takes into account the direction of the lee wave crests and had some success with that. So that was one method we used. But then another method we used was a Lagrangian filter developed by Shakespeare et al. 2021, which is a really nice method for filtering for waves in the frame of the flow. So you take the superinertial signal in the frame of the flow, and you call that your internal wave field. So that pulls out the lee waves and also other types of internal waves. And this is what happens if you do that. So these are the filtered wave fields. Again, at the top, the zonal velocity, and at the bottom, the vertical velocity. And you can see the vertical velocity hasn't really changed much. So lots of what was there before was internal waves. But the zonal velocity, it's really pulled out the internal waves. There's a factor of 10 difference in the color bar as well. Okay, so then we have a set of filtered wave fields. What about the parameterizations? So the key idea here is that when you have some large scale topography, the flow doesn't see the whole topography because energetically it can only really go over the top portion, otherwise it will just have to go round or it will get blocked. So the flow is blocked or split when the Froude number, NH over U, is greater than some critical value. And this is a concept that's been used a lot in the oceanic and especially the atmospheric literature. And that critical Froude number is kind of order 1. So the idea is that the flow sees an effective topography, which is U over N times some critical Froude number. And that's the topography that we want to represent and put into our parameterization rather than the full topography. So the two methods that we used of doing this, the first method I'll call the spectral method, and this is similar to what the methods that are currently used in lee wave estimates. So you take your full topography, H of X, Y, and that could be the black profile here, for example. Then you remove your large horizontal scales that don't generate propagating waves with a high pass filter. And then you scale the heights so that the root mean square height is such that the Froude number is less than the critical Froude number. So it's a kind of saturation idea, similar to for the internal tides in the last talk. And if you do that to this black profile, you might get something that looks like this blue profile here. So you can see that's going to be then your effective topography. But then the method that we developed, where we wanted to really kind of physically represent the effective topography, taking into account those ideas about blocking. So we take the black profile and then we find the peaks using a peak finding algorithm, fit Gaussian curves to those peaks. We then reduce the Gaussian height to account for that blocking. And that would give us, say, these little red caps here. And then we calculate energy flux from each peak. So the difference in representations is between this blue line here and between these red caps. So you can see there's quite a difference there. And just quickly, some results. So before looking at the energy flux, I'll look at the near bottom vertical velocities. So on the left, this is from the simulation. In the middle, that's from the peaks method. And on the right, that's from the spectral method. And so we're looking at 30-day and bottom 500-meter mean vertical velocities. And you can see that the peaks model captures quite a lot of the local features of the flow and the magnitude of the vertical velocity quite well, whereas the spectral method actually overestimates it quite a lot. And we might expect that from the way that the spectral method is devised. So that's the vertical velocity. And then finally, just a comparison of the energy flux between the model and the two parameterizations. So on the left here, I'm showing the domain and timing energy flux against the critical Froude number, which is kind of like the tunable parameter in our parameterizations. And in blue is the spectral method, in red is the peaks method, and in gray is the estimated energy flux from the simulation. So you can see there's kind of an error bar there, some uncertainty, and that doesn't change with the critical Froude number because that just affects the parameterization. So you can see they have much higher energy generation from the spectral method than the peaks method. It's around 3.5 times larger, a critical Froude number of 0.4, which is what it's kind of typically estimated to be. But the peaks method does agree quite well with the simulations at a critical Froude number of around 0.3 to 0.4. And then just on the right, I'm showing the domain mean energy flux against time. And you can see that both parameterizations kind of follow the temporal variability of the flux from the simulations quite well. But again, the spectral method seems to be overestimating it quite a bit. So just to summarize, we compared realistic simulations of lee wave energy flux in the Drake passage So linear parameterizations with two different representations of topography, the kind of typical spectral representation and our peaks representation. And we found that the peaks method better predicted the energy flux and root mean square vertical velocity, which over-predicted by the spectral method. And so it might be a better representation, especially when the topography is rough and when there's a lot of flow blocking. And this could account for microstructure observations in the Drake Passage region that suggest that Lee wave dissipation is significantly less than is predicted by linear theory. And then something I didn't talk about is that the peaks method actually implies that you have much higher Froude numbers of the topography, so much more nonlinearity in the wave field than the spectral method does. And that implies that the wave generation in this regime is more nonlinear. So you might have different routes to mixing than by kind of typical linear wave breaking, where we think about wave-wave interactions, for example. So you might have kind of convective overturning and so on instead. And that's everything. Yeah, thank you.